take a look at some problems of a geometrical nature. So in this one we have water is flowing, water flows into a cylindrical container at a rate of 5 cubic inches per second. Let's draw a container. And so the idea here is that we are pouring in 5 cubic inches per second of water. How big is our container? Our container has a height of 6 inches, and it has a base radius of 2 inches. And so the question is, at what rate is the water level rising? So right here, let's say this is how much water is currently in there, and the height of the water in our cylinder is h, and so we're trying to figure out how fast is h changing if this is how much water, 5 cubic inches per second, we're pouring in. Okay, so to take a look at our chart of our list of things to do. So step 1 is that we have to identify the variables and the rates that are related. So what do we have? We have information here about, we want to think about volume, which is V. That's how much water is in our cylinder at the time. We're given information here. We're given information. This is dV dt is what is one of the inputs of information. And the thing that we're trying to look at is this h here. We want to find dH dt. So our most important things here are h and v, and we're trying to relate together dH dt and dV dt. So let's do that. So step 2 on our list is find an equation relating the variables. So our equation is, well, V is pi r squared h, where that pi r squared, that's the area of a circle, and to find the volume of the cylinder, we multiply it by the height. Now in this problem, let's realize here, it might look like we have 3 variables, V, R, and h, but our r is staying fixed at 2 inches. So we should replace this. I'm going to drop units. So this is really pi times 2 squared, so 4 pi h. So now we're at the stage where we can differentiate this. So the second half of our step here, second half of our second step is differentiate, and as usual, we're differentiating with respect to time. And so on the left is just dV dt, and on the right we get 4 pi dH dt. And so here we see we have a relationship between dV dt and dH dt. There is just a constant multiples of each other. And so for us to look here what's going on, 5 cubic inches per second is our dV dt. So 5 is equal to 4 pi dH dt. Rearrange that to get dH dt is equal to 5 divided by 4 pi, which is, if you crunch that out, that is about 0.4 inches per second. So what is this saying? This makes sense that as we're pouring in, that we have a cylindrical container here, and we're pouring in water at a constant rate. The height of the water is going up at a constant rate. So let's ask the question of, well, what would happen if we had some other shape? So what would happen if instead of having a cylinder, we have a container that looks like a cone? So let's draw that. So it's still going to have a circle base to it. And we're still putting in water at a rate of 5 cubic inches per second. and our container has a height of 4 inches, and the base had a radius of 2 inches. And so our question here, once again, is, let's say that here is our water level. Let's call this H here. The question is, as we're putting in 5 cubic inches per second of water, how fast is the height of our water level inside our container changing? So note that this is a different problem than before. The most important difference here is that our container, like our cone, is going to get skinnier as we go towards the top. And so as we're going to see, as we pour in more and more and more water, it's actually going to, because it's a skinnier container, we're going to be putting in less, it will take less to increase the height. The height's going to increase more rapidly as we go on. So to look at our chart of things to do, identify variables and the rates that are related. So as usual, we have volume with V, and we're given dV dt is 5, and H here, that height, that's what we're trying to find, or more particularly, we're looking for dH dt. So that's the setup. So now we have to find the equation relating the variables. And this is going to be the most intricate part of the analysis. So you want to pay close attention to this. So what's going to happen? Well, we have some, let me draw a cone here. And so we are looking for, here is our volume that we want. And so the question is how to find the volume of the water at this point. Well, this is a kind of weird geometrical figure. And so the best way for us to think about it is to, let me draw this 2 more pictures. So this much water we can find is just the whole cylinder, or sorry, not cylinder, a whole cone minus what's up top. And so in order to find the volume that we care about, we have to find the volume of the whole cone minus the volume of the top, what's up here, what's not filled up. That will get us to what we want. So if you recall, in this case, our radius is 2, and the height is 4. So volume is, in general, it's going to be, volume of a circular cone is going to be 1/3 pi times r squared times the height. So in this case, that's going to be 1/3 pi times 2 squared times 4, or 16/3 pi. So that's the volume of the entire thing. So now to find the volume of the actual water, we have to find the volume of the very top of our cone, the space above the water. And so for this volume, so it's again going to be, let me call this RS and HS here. The volume is 1/3 pi times RS squared times HS. So now we just have to think about, in this particular problem, what's RS and what's HS. So HS, if we go back to our picture here, H is the height of the water, the overall height is 4, and so the height of the space above the water is going to be 4 minus H. So HS is going to be 4 minus H, and that's because the whole height is 4, the height of this water is H, so 4 minus H gives us 4 minus H. So we can plop that in for HS. And then to figure out what RS is, what we have to do is that we have to realize that we're going to use similar triangles here. That this and this are similar triangles. So the ratio 4 to 2 is equal to the ratio of HS to RS. In other words, rearranging this, RS is going to be 1/2 times HS, but we just said HS is 4 minus H. So this gives us all the information we need to fill in our volume. So 1/3 pi, RS is 1/2 times 4 minus H, all of that squared, and HS itself is 4 minus H. Okay, so at this point then, what do we have? It looks like we have a pi, then we're dividing by 3 and 2 factors of 2, so that's 12, and then we have 3 factors of 4 minus H. So what is our volume? It's this minus this. Okay, so let's go to the next slide to copy that down. Our volume is 16/3 pi minus the volume of the space above, which is pi 12 times 4 minus H cubed. Okay, so we have finally finished off that first step of part 1. Sorry, of part 2 here. So this took up a lot of work to figure out, find our equation relating the variables. Now we have to differentiate this. As usual, we're differentiating with respect to t. And so what's going on is, well, let's see, we have dv dt right here. Then we take the derivative with respect to t of this side. Well, 16 pi over 3, that's a constant, so that's 0. So minus pi over 12 times the derivative of this with respect to t. And I think we're going to be using, so let's just do that here. So this is going to be, we'll use the chain rule here. So that 3 comes down, 4 minus h squared, and then we have to multiply by the derivative of what's inside. So there's a minus 1, but then also we have to take the derivative of h with respect to t, again, by the chain rule kind of stuff. So what do we end up with here? dv dt is 3 over 12, that simplifies down to 1 over 4. There's a minus sign that comes out. So here we see that dh dt and dv dt, the relationship between them does depend on the height. So how fast is volume change? Sorry, we should say here how fast is the height changing. If we rearrange this, dh dt is equal to dv dt divided by all this stuff. So that's times 4 over pi divided by 4 minus h, all of that squared. And the last thing to do is that we remember dv dt in this particular problem was 5. So we end up with 20 over pi times 4 minus h squared. So here's our final answer for how fast our height is changing, and we see that the rate at which the height is changing, it depends on the height of the water in there already. So the higher h is, the bigger h is, the smaller 4 minus h will be, which will be a smaller denominator, which will be an overall larger rate and change. And so that matches our intuition from what the picture was. So the higher up we are, the skinnier the cone is, and so we'll be increasing our height even more and more quickly. Okay, so that's what's going on in this kind of problem. So this very geometrical one, where we have to use either formula for volume of a cylinder or volume of a cone. And so for the problem I want you to look at is here's the second pre-class problem. So assuming the radius r of a sphere is expanding at some given rate, find the rate of change of volume. And so your very first step here would be to write down an equation that relates volume of a sphere together with the radius, and you differentiate that to start this off. Okay, so that wraps up this video.